Good. If you like, we can continue. So what I'm going to do next is to give you more of the formal structure of stochastic processes. Up to now, I've been very loose in terms of, defining concepts and basically applying to your intuition on what probabilities are and how you define a master equation. So let's start with this new chapter, which I call Fundamental Equations for Markov processes. And what these Markov processes are, I will define. The first equation we would like to look at is named after Chapman and Kolmogorov. And it deals with defining for these Markov processes that I still have to define an equation of motion for conditional probabilities. So let's start very formal. But let's say I have a random variable, and this is a vector-valued random variable that has entries x1, x2, etc. And they're all random variables, so they take values as a function of time, and they can be either continuous random variables or they can be integers. Both is possible, and both we study. I will use a language where I'm basically talking about continuous random variables, but it doesn't really matter. If you go from continuous to discrete and back and forth, it's basically replacing sums by integrals and back and forth. So there's no real difference. And I also would like to write it down just for a single stochastic variable, so not for a vector. And the reason is basically simplicity. If I would write it down for a vector, I just have an endless set of equations that specify all the conditions. So it's not really restricting in any way the generality of what I do by looking at a single random variable that I call x of t. Okay, now in order to characterize that single random variable, I'll set up a probability density for it to take values, and this is now lowercase xn at time tn, take the value xn minus 1 at time t n minus 1, etc., and take the value x1 at time t1. Okay? And I call this a probability density, and when I multiply by the width of corresponding intervals that I call dx with a corresponding subscript, so dxn up to dx1, that is then my shorthand notation for the probability of all these variables that you see here being between x and x plus dx. So formally, I want this to be between xn, x of tn, and xn plus dxn, etc. I could just list all the different variables, the different time points that you have here. So the way you should think of this is you have a random variable, think of a position of a random walker. You make measurements. These measurements are at specific time points, t1 through tn. And at each of those measurement points, you ask yourself, what's the probability of finding my random variable at a certain position for that? And maybe the best way of visualizing that is to plot this in space, like so. So let's say here I have my random variable, and here is time, t, and I do have a random process, and forgive me of how I draw it. This is, of course, not a realistic description, so something like this. This is some random trajectory that you have. This is a single stochastic trajectory. And now you define certain measurement points. So here, time t1, time t2, really as you like it. Time tn, it's up to you whether you make them equidistant or at some other distance. It's how you would do the measurement if you were to do an experiment. And now you say, you look at a certain time point and you define a certain window. So here from x1 to x1 plus dx1, so that kind of window here. And you ask yourself, how likely is it that you pass through this interval that you define? That's what I mean by this probability. Okay. Then you can also write this for a discrete variable, and I won't do it, but you would write the same thing on the left-hand side. You would not write the d-axis, because this then is a probability itself. And you would say that xn equals a certain number, like the number of individuals in a certain population. Okay. Number of predators, number of prey, and then you would have a probability and not a probability density. That's the only difference. Okay, but let's leave it with this. We can also define a conditional probability. So this is kind of asking a question of, say you know that the system at given time points has taken certain random variables, and you want to know what is the probability distribution function of other time points given that knowledge. That's a conditional probability. So I can write this down. I want to know the probability density of having the values xn plus m at some time tn plus m up to the value xn plus 1 tn plus 1, conditioned on that I know that my random variable has taken all these values from x1 to xn at times t1 through tn at some previous times. And that, by definition, in probability theory, that's the probability of the whole joint distribution from x1 through xn plus m divided by the probability of the condition. So this is p, now really a lengthy expression, xn plus m at tn plus m all the way down to x1 t1 divided by the probability from x Tn up to T1. Okay? That's just definitions on the board. This should not get you confused. It's just what probabilities are and what some fundamental properties of probabilities are. Now comes the key point or key assumption, namely the assumption that these processes that I want to consider have a property that's called the Markov property. And it's a statement about conditional probabilities. And the statement is as follows. You do have a probability of finding the value xn at time tn given a whole sequence of events at some previous times, so many of them from x, taking the value xn minus 1 up to taking the value x1 at time t1. So the whole history of the process. I'm only interested in the probability of this random variable at time tn, condition of what happened earlier. Markov means that I'm assuming out of the whole past, the only thing that really matters is the immediate past. Okay, so I say, this is what Markov process means, that this conditional probability does only depend, as I said, on the most recent event at time tn minus 1. And all the past is not relevant for the process. We had examples like that. So the Poisson process, the random walk, the population dynamics process, those were all processes that had the Markov property, because otherwise I could not have talked about rates from a given state into a new state, because that assumes that the state I'm in is all the information I need in order to calculate the conditional probability into the next state. Okay? So I'm in a way, and this is now metaphorically speaking, I'm considering processes that have no memory. They start anew, with each new configuration, this is a new game, and you reiterate that new game over and over again. Okay, so let me call this in quotation marks. These are memoryless processes. Good. So we have that. And once we have this, there's consequences of this Markov property. And what I'm going to do, so you see kind of the trajectory I'm heading at with this analysis, I want to derive from that Markov property that we have master equations. Before, when I talked about master equations, I basically assumed in the background without mentioning that there is a Markov process and that can do that. Now I want to really formally show this based on the Markov property of my stochastic process. All right, now let's calculate the probability, and now to do a shorthand. So for that n here, what I mean is the value of my random variable at time tn. And I'm writing this in this shorthand notation. And I want the joint probability of having this sequence of events at times t1 through tn, taking values x1 through xn. So let us now use the Markov property. And first, before I do that, let me use the definition of conditional probability. So that's the thing I wrote down on the bottom. So this joint probability distribution function, using the definition of conditional probability, is the conditional probability n conditioned on all the previous events times p of n minus 1 through 1. Okay, so that's definition. There's nothing assumed here. This is the property of probabilities. But now that we have the Markov property from this first term, we don't have to consider anything beyond n minus 1. So that's the same because of my Markov property as p n minus 1, p n minus 1 to 1, right? And now I just repeat what I did here. I write this object now as a conditional probability times a probability. So using the definition of conditional probabilities, this is p of n minus 1 conditioned on n minus 2 up to 1, p from n minus 2 up to 1. And you see now how this game repeats. So here, again, I can completely ignore anything beyond n minus 2, meaning that this is p n minus 1, p n minus 1, n minus 2. And I guess now you can do this in your head. This goes on and on. So up to the point p to 1. And then I have here as the final element, closing it, p1. And that's a beautiful mathematical structure because it means if I know the one-time probability, p1, at time t1, I can propagate it by these conditional probabilities up to any point I like. And the propagator of this theory is the transition probability densities. Okay, so let me write this in words. One can propagate the one-time probability P1 by the transition probability densities Pj j minus 1. Okay. And that's the only objects that now matter. I don't need to know the full distribution function because I can reconstruct it. So the basic elements that this theory has is just the one-time probability and all of those conditional probability densities or transition probability densities as they go from one state to another state. All right? And you can now think ahead. I mean, propagator structures, you know, in field theory, you can write many differential equations in the propagator structure. And then you can use these kind of structures to define path integrals, and so you can do here. You can use this as a basis of defining a path integral description of your stochastic dynamics. That will come. Just wanted to mention it here because for those that know that structure, it might be illuminating. Now, I didn't talk about this Chapman-Kolmogorov equation yet, but I will do now. So we'll now use the Markov property to derive the Chapman-Kolmogorov equation. And it's an equation that characterizes one of those objects, namely this object, the transition probability density. We want to know an equation of motion for that, right? Because this is just a formal structure relating a set of probabilities to another set of probabilities. In reality, when you want to make a model for a real-life system, you need to know some equation for the objects that we have here on the board. And the main object really is what are these transition probability densities and how do they evolve in time. Good, so let's start. Let's start from a situation where I have two times x1, t1, x3, t3, and now think of an intermediate time in between. So let me draw this. We have here again our time variable t. Here we have time t1. Here we have time t2. And here we have time t3. And on that axis, we have our random variable. And now I'm looking at the object that I want to know what's the probability for me being at x3 at time t3 and the probability of being at x1 at time t1. Okay. This probability you can derive from a higher order joint probability distribution function, one which includes the information about the intermediate point at time t2 and integrates over it. That's known as marginalization, but it's really nothing but the fact that you can decompose probabilities, and then as you sum over it, you can recover the original distribution. So you have this joint probability distribution at these various time points that are fixed. Those are my experimentally determined time spots where I make the observation. And I now integrate over all the observations made here at this time point t2. That's why I have this integral over dx2. And then, of course, I need to recover the probability of being at x1 and x3 at times t1 and t3. Okay, that's called marginalization. And it's an exact relation. No approximation whatsoever is contained in that. Okay. Now that I have that, I rewrite both the left-hand side and the right-hand side in terms of this propagator structure that we have here. Okay, so I can write the left-hand side as p of x3, comma t3 conditional on x1 and t1 times p at x1 t1, okay, using the definition of conditional probability. And I can do so also in between. So it's integral over dx2. And now as you look at that structure, right, what you can do is just read this here from 1 through 3. And what you will get is P1, P1, 2, 2, 3. So what you have here then is P of x3, t3 conditional on x2, t2, P of x2, t2 conditional on x1, t1, P of x1, t1. And now we can cancel the one-time probability density because it appears in the same way on the right and the left-hand side. And what we remain with is this equation that I underline for the conditional probability densities. It's a bit of an awkward object if you read it. It's not really giving you what P of x1 of this object is. It's giving you an interrelation between all these conditional probabilities. So it's a functional consistency relation for the conditional probabilities that needs to be valid for systems that obey the Markov property. And that's the Chapman-Kolmogorov equation. The way you can visualize this is if you are here at this point and here at that point, you have trajectories that go from my initial value over this intermediate value to my final value. And what this says is that the transition probability from 1 to 3 can be dissected into a sum of conditional probabilities from 1 to 2 and then from 2 to 3, summing over all the possible intermediate points. Okay. And that's helpful because you can dissect things. And the idea then later is to make a very, very fine dissection of my process. And then by doing such a fine dissection of time, you can derive a differential equation in time. Questions? Good. I have just 5 minutes. So let me at least start with a case of discrete random variables and write it down. So in that case, the integral becomes a sum, and my Chapman-Kolmogorov equation is just the sum over all intermediate values going from the intermediate value to nt and going towards the intermediate value from the initial value n naught. So as I said, I now want to make things continuous in time. And I want to derive an equation for my system. So I want to have a differential equation for my probability density at some given time tau, starting on some initial condition. Well, I can write this as a differential quotient. So I consider some small increment delta t in time. And then I write 1 over delta tau. And I have here p of n tau plus d tau conditioned on n naught t naught minus the corresponding expression at time tau given the initial time. That's not the only question I can ask. I can also condition on the final time. This is something I'll do then next week, but let's keep it now for this question. So I'm looking at what happens given an initial condition at some later time, and I'm writing this in this differential quotient form. That's then called the forward master equation that we will derive, and there's a corresponding, as I said, backward form. So let me define an object mathematically, and you see in a second of why this is important. So I have two states, n and m, and I want to define Q as the object of 1 over delta tau P of n tau plus delta tau given m at time tau minus Kronecker delta nm. And I want a limit of that object where delta t goes to 0 So that's the limit of d tau going to 0 of q tau d tau nm. I need a few more minutes to finish that. So these are the mathematical objects that we want. And this object here is called the transition rate matrix, or just transition matrix. And now let me look at the matrix elements of that, namely first at the off-diagonal elements, where n is not equal to m. Well, in that case, I call this W tau of n and m. This is the same as my Q tau of n and m. And because now n and m are different, the last Kronecker delta term is, of course, 0. So you do have P of n at some small time later. Sorry, this is tau, given the value m at time tau divided by d tau. And that has now an obvious interpretation. This is the transition rate for my process, because it's the conditional property of going from m to n in a small increment in time. Okay, so that is what we call a transition rate. And we will often also write this as W of m going to n at time tau, because this is a transition rate from the state m to the state n. What about the diagonal elements? So what about n equals to m? Well, in that case, the W tau of m, by definition, is now minus q tau. That's how I define it, mn. So I take this object to be minus the diagonal elements. And I should replace the n by an m here. So that's now, by definition, the limit of delta tau going to 0. And that's 1 minus, because of the Kronecker delta, Pm at time tau plus d tau, given m tau, divided by d tau. So what is that? It's 1 minus, right? 1 minus the corresponding probability. So this is the probability of staying in the state. It's the complement. Okay, so that's the, how would I call this? Okay, so this is the probability of staying, and then one property that follows from that just has to do with the conservation of probability is that q tau nm equals 0 if you sum over all the possible final states. Yeah?
So I'm a bit confused. The probability of m that tau plus d tau given m tau, isn't that a probability for it to stay at m?
Yeah.
Times so 1 minus is what would be for it to not stay?
Yeah, that's the exit times. Oh, maybe I said it wrong. So these are the exit rates, and you're fully right. This is the probability that the system actually exits from the state. And then you have these two different probabilities. One is the probability of exiting the state, and the other is the probability of all the different transition rates. And as you sum over all of those rates, you need to get equal to 0. And that's really this is because you have the sum over all conditional probabilities, P of n t plus delta tau, given some initial state. That needs to be 1 because something has to happen if you start from your state n. It has to either stay or exit that corresponding state. And matrices with this property we call Q matrix, and they, as we'll learn then next week, they fully define the stochastic process, and with that we can derive a corresponding master equation. So thank you for your attention. See you next week.